AJ Akshara Academy YouTube channel. In this session, I am going to discuss wave optics. In this Mallus law. If you like this video, please subscribe to our channel. Please share your valuable comments in the comment section. Okay, let us go to the today's session. Mallus law. If I naught be the intensity of the polarized light incident on the analyzer and theta be the angle between the transmission axis of the polarizer and analyzer, then the intensity of light transmitted through the analyzer is given by I is equals to I naught cos square theta. If A be the amplitude of the light transmitted through the analyzer and A naught be the amplitude of the polarized light incident on it, then A square is equals to A naught square cos square theta, or A is equals to, this can be written as A naught cos theta. If I be the intensity of the unpolarized light incident on the polarizer and I be the intensity of the light transmitted through the analyzer, then here this is I. This is I be the intensity of unpolarized light incident on the polarizer and I be the intensity of the light transmitted through the analyzer. Then I is equals to I by 2 cos square theta. So from this I is equals to I by 2, nothing but I naught. So I is equals to I naught cos square theta. Here I naught is equals to I by 2. In the above expression, theta is also angle between the plane of oscillation of the polarized light and the transmission axis of the analyzer. Next, for the crossed polarizer and analyzer, theta is equals to 90 degrees. Hence, I is equals to I naught cos square 90. So, cos 90 is equals to 0. So, I is equals to 0. Polarization confirms the transverse nature of the light waves. So, light can be polarized by the following methods: reflection, refraction, double refraction, dichroism and scattering. Now, discuss MCQs. Polarization confirms the dash nature of the light waves: transverse nature, longitudinal, both A and B, none of the above. So, polarization confirms the transverse nature of the light waves. First option is correct. Next, which of the following method can be used for polarization of light? Reflection, refraction, double refraction, all of the above. Here in these methods, which method can be used for the polarization of light? All the above. We can use reflection, refraction, double refraction. Okay. Now discuss Brewster's law. Brewster's law. Here taking the ordinary light and which is incident on the air. This is a glass and air glass interface. This is unpolarized light. Now you are taking the mirror and it is the angle of incidence. Part of light is reflected. This is the reflected light, while the rest is refracted. This is refraction. A certain angle of incidence known as polarizing angle. The reflected light is completely plane polarized in the plane of incidence. So, at a certain angle of incidence known as polarizing angle, the reflected light is completely plane polarized in the plane of incidence. Observe the picture. Such an angle of incidence of ordinary light at which the reflected light from the transparent medium is completely plane polarized is called as polarizing angle. Okay. Now I will discuss angle of polarization or polarizing angle. The angle of incidence of ordinary light at which the reflected light from the transparent medium is completely plane polarized is called as polarizing angle or Brewster's angle or angle of polarization. Okay. Next, at this point the reflected and the refracted rays are mutually perpendicular. This is reflected ray and here refracted rays. These are mutually perpendicular. Now we'll discuss proof of Brewster's law. According to Snell's law, mu is equals to sin I by sin R. Here sin I by R nothing but 90 minus R dash. So since R plus R dash is equals to 90 degrees, so that's why R is equals to 90 minus R dash. Now sin 90 minus theta cos theta. So sin IP by cos R dash. Cos theta is equals to sin of 90 minus theta. Sin IP by cos IP. In the place of R dash we are substituting IP. Okay, IP is equals to R dash. So therefore sin by cos, sin theta by cos theta, tan theta. So sin IP by cos IP it can be written as mu is equals to tan IP. Hence it is proved. Mu is equals to tan IP. Now discuss MCQs. First one. According to Brewster's law, mu is equals to sin I by sin R, mu is equals to sin R by sin I, mu is equals to tan IP and mu is equals to 1 by tan IP. So according to Brewster's law, mu is equals to tan IP. Third option is correct. Next, at polarizing angle, the angle between reflected and refracted ray is 0 degrees, 45 degrees, 180 degrees, 90 degrees. So at polarizing angle, the angle between reflected and refracted rays is 90 degrees because they are mutually perpendicular. Next, at polarizing angle, the incident unpolarized light is reflected as a plane polarized light, an unpolarized light, a partially polarized light, none of the above. So this at polarizing angle, the incident unpolarized light is reflected as a plane polarized light. Next, now we'll discuss Young's double slit experiment. Let's now discuss Young's double slit experiment. Thomas Young used an ingenious technique to log the phases of the waves emanating from S1 and S2. He made two pinholes S1 and S2 very close to each other on an opaque screen. These were illuminated by another pinhole that was in turn lit by a bright source. Light waves spread out from S and fall on both S1 and S2. See this picture carefully. This is the small slit and see the dark bright rings are forming in this picture, and from the two slits here S1 and S2, this is the screen, they are forming the dark and bright points. See this. This is the formation of alternatively dark and bright See, this is the one dark band and bright band. This denotes the bright point and this denotes the dark point. Now I'll discuss Young's arrangement to produce interference pattern. See, this is the pattern of the Young's arrangement, interference pattern. S1 and S2 then behave like two coherent sources because light waves coming out from S1 and S2 are derived from the same original source, and any abrupt phase change in S will manifest in exactly similar phase changes in the light coming out from S1 and S2. So thus the two sources S1 and S2 will be locked in the phase. So they will be coherent like two vibrating needles in a water wave. Next, thus spherical waves or spherical wave front emanating from S1 and S2 will produce interference fringes on the screen G, G dash. The position of maximum and minimum intensities can be calculated by using the analysis given that for an arbitrary point P on the line G, G dash to the corresponding to a maximum. So, S2P minus S1P is equals to n lambda, where n is equals to 0, 1, 2, etc. So, consider this equation number 1. Now, so this can be written as here S2P whole square minus S1P whole square is equals to d square plus x plus d by 2 whole square minus d square plus x minus d by 2 whole square is equals to 2xd, where S1, S2 is equals to d and OP is equals to x. Thus, S2P minus S1P is equals to 2xd by S2P plus S1P. Consider this as equation number 2. If x comma d is less than d, then negligible error will be introduced if S2P plus S1P is replaced by d. So, for example, for d is equals to 0.1 centimeter and capital D is equals to 100 centimeter, OP is equals to 1 centimeter, which corresponds to typical waves for an interference experiment using light waves. Then we have S2P plus S1P is equals to 100 square plus, substituting these values, 100 square plus 1.05 whole square whole to the power of half plus 100 square plus 0.95 whole square whole to the power of half. So that is equals to, after calculation, we are getting 200.01 centimeters. Thus, if we replace S2P plus S1P by 2D, the error involved is about 0.005%. So, in this approximation, equation 2 becomes S2P minus S1P is equals to xd by d. Consider this as equation number 3. Hence, we will have constructive interference resulting in a bright region when x is equals to xn, that is equals to n lambda d by d, where n is equals to 0 plus or minus 1 plus or minus 2 and so on, etc. This is equation number 4. On the other hand, we will have a dark region near x is equals to xn, that is equals to n plus half lambda d by d, where n is equals to 0 plus or minus 1 plus or minus 2 and so on. So, consider this equation number 5. Thus, dark and bright bands appear on the screen. Such bands are called fringes. So, these are called the fringes. When d is greater than or greater than d and white light source is used, then the wavelength absent in front of one of the source will be lambda is equals to d square by d, d square by 3d, d square by 5d. So, path difference, that is equals to d square plus d square, that is equals to d square by 2d of that point. So, path difference for dark fringes, d square by 2d is equals to 2n minus 1 of lambda by 2. So, the distance between two consecutive bright and dark fringes is given by beta is equals to xn plus 1 minus xn, or this can be written as beta is equals to lambda d by d. This is equation number 6, which is the expression for the fringe width. This is the expression for the fringe width. So, fringe width beta is equals to lambda d by d, where on putting n is equals to 1, 2, 3, the missing wavelengths d square by d square by 3d are obtained. So, if an additional phase difference of pi is created in one of the waves, then the central fringe becomes dark. Okay. The bright fringes are the result of the constructive interference, whereas the dark fringes are the result of destructive interference. So, bright fringes result of constructive interference. Dark fringes are the result of destructive interference. So, the central fringe is bright with monochromatic light, whereas it is achromatic white, achromatic nothing but white with the white light. The formation of fringes is explained on the basis of the Huygens wave theory of light. So, this formation of fringes is explained on the basis of Huygens wave theory of light. Now, discuss MCQs. First one, in Young's double slit experiment, sodium vapor lamp is replaced by the neon lamp. Then the fringe width, if you replace the sodium vapor lamp is replaced by a neon lamp, then what happens to fringe width? Increases, decreases, remains the same, becomes 0. So, the fringe width decreases. If we replace the sodium vapor by the neon lamp in Young's double slit experiment, the fringe width decreases. Okay. Next, a fringe is the locus of constant amplitude, constant intensity, constant phase, same wavelength. A fringe is the locus of constant phase. Third option is correct. Next, Young's experiment establishes that light consists of waves, light consists of photons, light consists of corpuscles, light has dual nature. So, Young's experiment establishes that light consists of waves. Thanks for watching this video.